Most e-bike owners think their battery died from old age. Actually, they killed it themselves. Today, we're breaking down the 10 habits that are silently destroying your battery right now, ranked from bad to catastrophic. The surprises on this list are genuinely disturbing. And the number one habit, it's something manufacturers actively hide in the fine print because they'd rather sell you a replacement battery every 2 years. That's a $700 mistake waiting to happen. Ignore this and you might wake up to a battery that won't charge, won't hold power, or worse, one that's become a legitimate fire hazard sitting in your garage. Here's what makes this video different. We're not recycling generic battery care tips you've seen 100 times. Every habit on this list is backed by actual failure data, consumer reports testing, CPSC recall documents, Battery University research, and thousands of owner forum complaints we've tracked across Reddit, Endless Sphere, and Electric Bike Review. Some of these habits cause damage you'll notice in months. Others are ticking time bombs that won't show up until year 3, right after your warranty expires. Convenient timing, right? Let's get into it. Number 10, running your battery to 0% before charging. This one trips up everyone coming from the NiCad battery era. You remember those old cordless drills that developed memory effect if you didn't fully discharge them? Lithium-ion cells work exactly opposite. Every time you drain a lithium battery to 0%, or what your display calls zero, which is actually around 32 to 42 volts depending on your pack configuration, you're forcing the BMS into emergency shutdown mode. Here's the mechanism. When cells drop below their minimum safe voltage, typically 2.5 volts per cell, the internal chemistry starts breaking down in ways that permanently reduce capacity. The copper current collector in the negative electrode can actually dissolve, creating irreversible damage. One Bosch battery engineer on the EMTB forums documented this clearly. Repeatedly hitting 0% can shorten total lifespan by 15 to 20% compared to keeping charge between 20 and 80%. But here's what manufacturers don't advertise. That 0% on your display? It's a lie. The BMS shuts down the pack well before the cells hit actual zero to prevent permanent damage. So when you're pedaling home on an empty battery, cursing your range estimate, you're not actually empty. You're just past the safe discharge limit the BMS will allow. The problem is the stress damage accumulates anyway. Keep doing it and you'll notice something interesting around charge cycle 300. The voltage sag under load gets worse, the pack can't sustain high current draws anymore, and that 30-mile range you started with drops to 22 miles, even though the capacity meter still shows 85% health. That's cell imbalance from repeated deep discharge stress, and it only gets worse from there. Number 9, storing your battery at the wrong charge level. Storage charge level is probably the most ignored specification in the entire e-bike industry, and it's costing people hundreds of dollars in premature battery replacement. Trek's engineering documentation, which most riders never see, states explicitly that storing a battery at full charge for more than 30 days causes approximately 20% capacity loss per year. Not over the battery's lifetime, per year. Store your bike in the garage at 100% all winter? You just threw away $150 in battery value. The chemistry explanation matters here. At full charge, lithium-ion cells sit at 4.2 volts per cell, which keeps the internal chemistry in a high-energy state that accelerates degradation reactions. It's like keeping a rubber band stretched for months. The material slowly loses its ability to return to normal. Battery University studies show that storage at high voltage corrodes the positive electrode material, causing permanent capacity decay that averages 18% annually. In contrast, storage at 40 to 60% charge, that's 3.8 to 3.9 volts per cell, keeps the chemistry stable and degradation drops to around 3 to 5% per year, which is just normal aging. Here's the scenario we see constantly on owner forums. Someone buys an e-bike in spring, rides it all summer, charges it to full so it's ready to go in the fall, then leaves it in the garage all winter. Come March, they pull it out and notice the range is terrible. They blame winter storage generally, not understanding they created a 6-month high-voltage stress test. Even worse is storing batteries depleted. Drop below 20% for extended periods, and you risk the BMS going into deep sleep mode, where the pack won't charge at all without special recovery procedures that void most warranties. The fix is dead simple but requires discipline. Charge to 60% for storage, check it every 2 months, and top back to 60 if it's dropped. Shops won't tell you this because they'd rather sell you a new battery in year 3. Number 8. Charging your battery immediately after riding hard. This habit reveals a fundamental misunderstanding about how heat affects lithium chemistry. After a hard ride, especially in summer heat or while using turbo mode constantly, your battery pack can easily reach 40 to 45 degrees Celsius internally. That's around 110 to 115 degrees Fahrenheit. Plug it into the charger immediately and you're asking for trouble, because charging generates additional heat through resistance in the cells and the BMS balancing circuits. The double heat exposure accelerates what researchers call calendar aging. A study posted on the electricbike.com forums showed that charging cells above 40 degrees Celsius degrades the electrolyte faster and promotes lithium plating on the anode, which permanently reduces capacity and increases internal resistance. Translation: your battery holds less charge and delivers less power. What's particularly sneaky about this damage is it compounds over time. The first 50 cycles you might not notice anything, but around cycle 200, riders start reporting on EMTB forums that their batteries feel weak on climbs or cut out under heavy load, even though the charge meter shows plenty of capacity remaining. If you're in a rush and need a quick top-up for another ride, at least give it 20 minutes. That's usually enough to drop from dangerous temps to merely warm. And if your battery case feels hot to the touch after a ride, that's your warning sign that you've been riding hard enough to need a cooling period. The cells inside are even hotter than the case exterior, sometimes by 10 to 15 degrees. Number 7. Using fast chargers for every charge cycle. Fast charging sounds great in theory. Bosch offers a 6-amp fast charger that promises to refill your battery in under 3 hours compared to 6 hours with the standard 2-amp unit. The problem is that speed comes with a cost your cells pay every single time. Research from Leoguar Bikes documented that frequent fast charging accelerates cell degradation by 15 to 20% over 500 cycles compared to standard charging rates. That's the difference between a battery lasting 4 years versus 3.2 years, assuming similar usage patterns otherwise. The damage mechanism is straightforward. Higher charge current generates more heat, and heat is the #1 enemy of lithium-ion longevity. But there's a second, more insidious problem. Fast charging stresses the final 20% of the charge curve more than slow charging does. You'll notice this if you pay attention. Your fast charger probably runs warm during the first 80%, then gets noticeably hotter during that final push to 100%. That's because the BMS has to work harder to balance cells and manage voltage as they approach full charge. The hotter it gets, the faster the electrolyte breaks down chemically. Some owner forums suggest using fast chargers no more than 2 or 3 times per week if you want your battery to survive past the warranty period with decent capacity. Beyond that frequency, you're essentially choosing convenience today over battery replacement costs tomorrow. Number 6. Exposing your battery to constant vibration and impacts. Here's a damage vector most riders completely ignore until it's too late: mechanical stress. Lithium-ion cells aren't solid-state devices. They contain liquid electrolyte and extremely thin separator membranes that can be damaged by repeated vibration and impact. A research paper published in the Journal of Sound and Vibration showed that battery packs subjected to sustained vibration testing, equivalent to 100,000 miles of vehicle use, demonstrated significantly increased internal resistance and reduced capacity. E-bike batteries face similar conditions, especially on rough terrain or when mounted on car racks for transport. The car rack scenario deserves special mention because it's so common and so damaging. Tossing your e-bike on a trunk rack, battery still mounted, then driving 300 miles to your vacation spot? Every bump, every highway vibration is stressing those cells and their connections. Smart riders remove the battery before transport and carry it inside the vehicle where it's protected. Same logic applies to riding style. If you're constantly hitting jumps, riding over roots and rocks, or generally treating your e-bike like a motocross machine, you're accelerating mechanical degradation. Some battery cases are better protected than others. Bosch power tube batteries mounted inside the down tube fare better than rack-mounted soft-pack batteries. But no battery is immune to sustained mechanical abuse. The fix is mindful riding and proper transport practices, neither of which cost money, but both require changing your habits. Number 5, ignoring battery management system error codes and warnings. Your BMS is trying to tell you something, and most riders just clear the error and keep riding. This is catastrophically bad judgment. When your display shows codes like E21 for voltage fault or E06 for low battery, those aren't suggestions. They're warnings that your battery's protective systems have detected conditions outside safe operating parameters. Ignoring them is like ignoring your car's check engine light because the engine still runs. Sure, it works now, but you're accelerating toward complete failure. Here's what happens behind those error codes. The BMS continuously monitors dozens of parameters: individual cell voltages, pack temperature, current draw, charge state. When something exceeds safe limits, it throws an error and usually cuts power to protect the pack. A low voltage cutoff means one or more cells drop below the safe discharge threshold. A temperature error means the pack got too hot. An overcurrent error means you demanded more power than the system can safely deliver. Each of these represents actual damage occurring in real time. Clear the code without addressing the root cause, and you're just resetting the warning system while the underlying problem continues. The correct response to persistent error codes is immediate diagnosis. Check all electrical connections for corrosion. Look for physical damage. If the error persists after cleaning connections and ensuring the battery is properly seated, take it to a qualified technician before the problem cascades into battery replacement territory. Number 4, riding and storing in temperature extremes. Temperature is the silent killer of lithium-ion batteries, and the damage occurs at both extremes. The optimal operating range for e-bike batteries is 15 to 25 degrees Celsius. That's roughly 60 to 77 degrees Fahrenheit. Go significantly outside that range in either direction, and you're degrading your cells faster than normal aging would predict. What makes this particularly insidious is that temperature damage often isn't immediately obvious. You'll ride all winter in below freezing temps, notice the range is terrible during rides but recovers when warm, and assume that's just temporary. Wrong. You're causing permanent damage. Cold damage works through a specific mechanism. When the electrolyte gets cold, it thickens, slowing the movement of lithium ions between electrodes. This creates higher internal resistance, which reduces available power and range. But here's the permanent damage part. If you ride hard in the cold, demanding high current while the electrolyte is viscous, you can cause lithium plating on the anode. This is where lithium metal deposits form instead of properly intercalating into the electrode structure. Lithium plating reduces capacity permanently and can eventually create dendrites, tiny metal whiskers that grow through the separator and short-circuit the cell. One owner on Endless Sphere documented losing 30% capacity over 2 winters of sub-zero riding, even though the battery showed no damage when warm. The cells had accumulated so much lithium plating that their effective capacity dropped permanently. Heat damage is equally destructive but faster. Temperatures above 40 degrees Celsius accelerate every aging mechanism in the battery. The electrolyte breaks down chemically. The electrode materials degrade. The separator membrane weakens. Battery University data shows that storage at 45 degrees Celsius doubles the aging rate compared to storage at 25 degrees Celsius. Translation: leave your bike in a hot car or garage all summer, and you're burning through battery lifespan twice as fast as necessary. The extreme scenario is thermal runaway risk. If you charge a battery that's sitting in direct sunlight on a 95-degree day, internal temps can spike past safe limits, and in rare cases this can trigger a cell failure that cascades into fire. CPSC has documented multiple fire incidents linked to high-temperature charging. The fix is boring but effective. Store your battery indoors where it stays moderate temperature year-round. And if you must ride in extreme heat or cold, minimize the ride duration and give the battery time to return to normal temps before charging. Number 3, leaving your battery at 100% charge for extended periods. This is where we separate casual riders from people who actually understand lithium chemistry. Keeping your battery at full charge seems logical. It's ready whenever you want to ride. But every hour your pack sits at 100%, You're accelerating degradation through a mechanism called high-voltage stress. This isn't speculation or manufacturer paranoia. Multiple studies, including published research from Battery University and real-world data from Tesla's electric vehicle battery management, show that prolonged storage at full charge causes measurably faster capacity loss than storage at moderate charge levels. The chemistry is surprisingly straightforward. At 4.2 volts per cell, what your charger calls 100%, the lithium cobalt oxide, or NMC cathode material, is in its most oxidized, highest energy state. This makes it chemically reactive and prone to breakdown. Think of it like keeping a rubber band under maximum tension continuously. Eventually, the material fatigues. One study from Happy Run documented battery expansion rates after 300 charge cycles. Batteries that spent most time at 100% charge showed expansion rates of 37%, while batteries managed according to manufacturer recommendations, charged to 80% for daily use, only going to full for longer rides, showed expansion under 5%. Swollen batteries aren't just cosmetic problems. They indicate internal damage that reduces performance and increases fire risk. Here's what kills people on this one: the ready-to-go mentality. They finish a ride, plug into full charge, leave it plugged in or sitting at full for 3 days until the next ride, then repeat. That battery spends maybe 3 hours per week actually discharging and 165 hours sitting at maximum voltage stress. Over a year, that's roughly 8,000 hours at full charge versus maybe 150 hours actually being used. The capacity loss adds up fast. Many Bosch users on EMTB forums report that leaving batteries at 100% between weekly rides drops capacity to 80% by year 2, whereas riders who charge to 80% for daily use and only go to full before long rides often see 90% capacity at year 3. The difference is literally thousands of hours of high-voltage stress. If you only ride weekends, charge to 80% after your Saturday ride, then top to full Friday night before your next ride. You'll add a year or more to your battery's useful lifespan, guaranteed. Number 2, charging a frozen or below freezing battery. This is one of the few battery habits that can cause instant, catastrophic, permanent damage. When you charge a lithium-ion battery below 0 degrees Celsius, 32 degrees Fahrenheit, you're not just reducing performance. You're fundamentally breaking the cell's internal structure through a process called lithium metal plating. This isn't theoretical damage that might show up later. This is immediate, irreversible capacity loss, plus a serious fire risk that accumulates with each frozen charging session. The mechanism matters here because it explains why quality chargers won't charge cold batteries. When lithium ions move during charging at freezing temps, the sluggish electrolyte can't transport them efficiently into the graphite anode structure. Instead of intercalating properly between the graphite layers, lithium metal plates out on the anode surface. These metallic deposits reduce the cell's lithium inventory permanently, cutting capacity. But the real danger is dendrite growth. As metallic lithium accumulates through repeated frozen charges, it can form sharp crystals that eventually pierce the separator membrane and short-circuit the cell. This is how internal short circuits develop that lead to thermal runaway and battery flares. Multiple manufacturers explicitly warn against charging below freezing in their manuals, the documentation everyone ignores. Bosch chargers have temperature sensors that refuse to charge if the battery is below 0 degrees Celsius. Trek states clearly that charging below 32F will irreparably degrade cells. But cheap chargers, including many aftermarket and universal models, lack temperature sensing entirely. They'll happily pump current into a frozen pack, and the owner won't know they've damaged their battery until months later when the capacity mysteriously drops or the BMS starts throwing errors. The winter scenario is depressingly common. Rider brings bike in from below freezing garage, immediately plugs in to charge, gets 20 minutes into the charge cycle before realizing the battery was still frozen inside the case, even though the garage is warm. By then, lithium plating has already begun. The correct procedure takes patience. Bring the battery inside, let it sit for 1 to 2 hours until it reaches room temperature, then charge. If you're in a rush, at least let it warm to 10 degrees Celsius before charging. That's roughly 50 degrees Fahrenheit. Anything colder is asking for permanent damage. Number 1. Using cheap third-party chargers and non-OEM batteries. Here's the habit that lands at number 1, because it combines fire risk with rapid battery destruction, usually while voiding your warranty and potentially your homeowner's insurance. The e-bike fire statistics are genuinely disturbing. UK Office for Product Safety and Standards data shows nearly 50% of e-bike fires involve third-party or modified battery packs and low-cost chargers. CPSC issued warnings specifically about universal chargers that lack proper safety cutoffs. The Rad Power Bike's battery recall, 31 fires, over $700,000 in property damage, highlighted how even name-brand batteries can fail, let alone the no-name replacements people buy on Amazon to save $200. The problem is systemic. Cheap chargers cut costs by eliminating essential safety features. They lack thermal sensors to detect overheating. They skip the sophisticated battery management communication that lets your OEM charger and battery negotiate charge rates safely. They use inferior components that can fail and continue delivering power even after the battery is full. This is how overcharging happens in the real world. A Los Angeles fire investigation traced an e-bike battery fire to a universal charger bought online as a budget replacement. The charger's voltage regulation failed, continued pumping current into a full battery, caused thermal runaway, and burned down an apartment. The owner survived but lost everything. Third-party batteries are even worse because you don't know what you're getting. That high-capacity battery advertised with Samsung cells might be genuine Samsung cells, might be counterfeits, might be B-grade cells that failed quality control and got sold to battery pack assemblers. You definitely don't know if the BMS is properly programmed for the cell chemistry. A mismatched BMS can allow overcharging, over-discharging, or fail to properly balance cells during charging. All of these lead to accelerated degradation and increased fire risk. Electrical safety. First found nearly 60 listings of substandard e-bike chargers for sale through third-party online sellers, none of which meet basic safety standards. The cost argument falls apart under scrutiny. An OEM charger costs $150 to $200. A cheap universal replacement costs $40 to $60. You're saving roughly $100. But if that cheap charger damages your $700 battery through poor voltage regulation, and owner forums show this happens regularly, you didn't save money. You spent an extra $600. And if it causes a fire, your insurance claim gets rejected because you used non-certified charging equipment, and suddenly you're fighting a 5-figure property damage bill. The math doesn't work. Buy OEM chargers and batteries, or at minimum buy UL2-849 certified replacements from reputable suppliers. The certification means the entire electrical system, battery, charger, controller, was tested together and passed safety standards. Yes, it costs more upfront. It also means your house probably won't burn down, which seems worth the premium. If you learned something here, check out our video on 13 electric bikes that look great but break instantly. We expose the models with known failure points, customer service disasters, and hidden reliability issues that reviewers won't mention. You'll want to watch that before you buy your next e-bike.